Hi everyone, and welcome to the webinar. Okay, here we'll be presenting a special condition monitoring and diagnostic solution for rotary cement kilns. Now the monitoring solution is based on a monitoring system specially customized for the application, together with a monitoring service with diagnostic supervision. Now the monitoring solution has already been successfully implemented, and we believe this success for this project is due to the combined efforts of FLSmith and Kjær Vibro, where each are sharing their particular expertise in their particular domain for this project. So I'm Mike, and joining me is Palle and Sascha, and we're going to talk about the comprehensive condition monitoring system and service solution for monitoring the rotary cement kiln. But let's first look at the agenda. First, we're going to begin with a brief introduction to the rotary cement kiln and the critical role it plays in the cement plant and the consequences that can occur when it stops working. We'll also talk a little bit about how FLSmith and Kjær Vibro join forces to address this issue. Then we'll go in more detail about the potential failure modes of the kiln and the monitoring techniques used for detecting and analyzing these. The kiln solution is based on an FLSmith service, which we'll present here when we get to it. And the monitoring strategy includes the monitoring system, of course, and data management and the cloud solution, which we'll also talk about. So there's currently several kilns being monitored with this monitoring solution, and we will share some of the results with you at this point here. And finally, we'll wrap it up with a conclusion. Alrighty. So the cement kiln is the heart of the cement plant, and its design capacity is what determines the total cement output of the plant. Traditionally, kilns have been stopped for inspections at frequent intervals, but nowadays this is considered much too costly. For efficiency and profitable production, the kiln typically needs to operate continuously for at least 1 year between maintenance shutdowns. Planned and unplanned shutdowns not only result in lost production, but the heating up and the cooling down process is also long and very thermally stressful. And this results in higher emissions, inefficient waste of energy, and a higher risk of maintenance issues with less sustainable operation. Now, in this webinar, we're going to talk about how kiln healthcare can be evaluated based on a continuous online condition monitoring system and service to minimize the frequency of the planned and unplanned shutdowns. Condition monitoring of kilns becomes even more important when, for example, alternative fuels are in operation, since the wear and tear becomes more difficult to predict in that situation using traditional maintenance and on-site inspections. And by just avoiding a single shutdown, this can result in a cost savings of upwards of €100,000 per day. This would be based on a typical 5,000 ton per day size kiln, and assuming a 24-hour lost production downtime due to the cooling down and the heating up procedures. And this doesn't even take into account the additional cost for maintenance and spare parts. Now, FLSmith and Kjær Vibro have collaborated in making a comprehensive online condition monitoring solution for cement kilns. FLSmith provided expertise on equipment design, operation, failure modes, maintenance, cloud data sharing, together with their existing monitoring techniques. And Kjær Vibro provided their technology and expertise on data acquisition and processing, together with optimizing measurement techniques for early and reliable fault detection. So that's our introduction to this webinar. And now Palle will talk about what can go wrong with the kiln and about the monitoring technique needed for fault detection and diagnostics. Palle?
Thank you, Mike. Yes, I'll explain a little bit some of the selected failure modes that our condition monitoring solution is covering, explain the theory behind it, why it's important, and most importantly, how we have managed to design the monitoring solution in order to continuously monitor these failure modes or these symptoms. The first thing I'd like to explain is what we call kiln shell ovality. Kiln shell ovality, that's a consequence of the design of the kiln. And basically what you see in this illustration is a cross-section of the kiln. The kiln is supported by typically 3 supports, but it can be up to 8 or 9 depending on the size of the kiln. Each support consists of a tire, as you see in this illustration, which is supported on 2 rollers. The kiln shell is suspended within the tire, and as seen in this photo, somewhat exaggerated, then there is a diametrical clearance between the outer diameter of the kiln shell and the inner diameter of the tire. This creates some collapse of the kiln shell, which creates shell ovality. This is actually a wanted mechanism, because as the kiln rotates, then we will need to have some room for thermal expansion between the kiln shell and the tire. Why we want to monitor the tire migration is that it can become either too high or too low, with related consequences on that. So in practice, what we do is we want to measure the rotational speed of the tire as well as the rotational speed of the kiln shell. Then, knowing the geometrical dimensions of all parts, we can actually calculate the travel of each of the items on 1 kiln revolution. Calculating then the difference on this, then we get a figure that we call tire migration. So tire migration is basically the relative slip or the relative movement between the tire and the kiln shell for 1 kiln revolution. From this, we can also determine the top clearance, as you see in this illustration, which is important in order to avoid constrictions. Constrictions is a dangerous failure mode that happens when the kiln shell expands until the top clearance is 0, and then due to the heating inside the kiln, the shell can continue to expand. This will cause constriction, which can lead to permanent deformations in the kiln shell and related failures in that. On the other hand, live ring migration can also become too high. This will cause excessive kiln shell ovality, which can cause failure and excessive wear on the kiln shell, and as well on the brick lining, which is a lining that's placed inside the kiln shell. Yes. Let's jump to the next one. Thanks, Michael. So the next failure mode that we are interested in monitoring is what we call Kiln Crank. Kiln Crank is a failure mode where the kiln does not rotate around its own axis of rotation. You could say that it is eccentricity of the kiln shell, or it is run out of the kiln shell. This issue can be caused either by mechanical erection tolerances, but it can also be due to thermal effects in the kiln. And the thermal effects is what's most relevant, because this is something that is changing over time, and this is something that is being affected by the operation of the kiln and the process inside the kiln. To explain a kiln crank, you can see it on this illustration. It is basically that the kiln is rotating like a crank-like shape. It could also be explained as a banana shape. So what will happen and why this is important to monitor? It is because when the kiln then rotates, then it will create cyclic overload on the supporting elements. This is especially the tire and the supporting rollers that support the tire. If the kiln continues to run with a kiln crank, then it can lead to fatigue failure in the supporting elements. And this is basically one of the most critical failure modes when it comes to breakage in the supporting rollers. Yes, Mike? So how do we monitor kiln crank? Again, what we want to monitor, that is the cyclic deflection of the supporting rollers. In this photo, it's illustrated that the kiln axis is rotating off center. So you can see it's kind of an orbit. The consequence of this would be that we have a cyclic deflection of the supporting roller. To monitor this, then we use inductive distance sensors positioned below each of the rollers. And from this, we detect the cyclic variation of the distance and the amplitude. And it is important to know that the reality is not as ideal as we see in this photo. So the roller here may not be completely cylindrical. It can have imperfections. It can have pitchings out of roundness. This we of course overcome by introducing some filtering techniques. So the only contribution that we get, that is the cyclic variation corresponding to the kiln speed frequency. And this is basically the deflection of the supporting roller due to the kiln crank. Based on empirical measures and on-site experience, we know what is the allowable limits for kiln crank measures like this. Yes, thanks, Mike.
Alrighty. Yeah, thanks for that, Palle. So kiln, ovality, and crank are serious issues to deal with. So okay, I'm going to talk a little about fault detection and diagnostics of the drive system part of the kiln. And this basically consists of the girth gear, the pinion, and the gearbox and motor that drive the pinion. The gearbox and motor are not shown in this slide picture here. Now, the girth gear and pinion for the kiln is unlike gears found on other machines, and it presents a significant challenge for both a maintenance and monitoring perspective. Firstly, the girth gear is more or less rigidly attached to the kiln shell, except for some tangential segment supports that allow for the shell to thermally expand during operation. So this means any kiln crank or ovality deformation present in the shell will directly affect the girth gear. And secondly, the pinion gear, by contrast, is rigidly mounted on the support foundation. This means any relative motion between the girth gear and the pinion will impact the pinion itself. And as shown in this figure, there can be a radial movement, wobble, and axial movement of the girth gear in relation to the pinion. This can result in improper gear meshing, variable gear tooth root clearance, and incorrect pitch circle alignment. This creates stress, and the stress will eventually lead to premature wear and failure. And moreover, as the gear teeth wear, this increases stress even more. And then, of course, lubrication problems can also accelerate the wear. Alrighty, so the girth gear is monitored by non-contact displacement sensors to determine the girth gear radial, axial, and wobble movement. And in this slide right here, we're looking at the monitoring strategy for monitoring the radial movement. Here it is important to not only monitor the so-called runout of the girth gear, but also its axis of rotation as shown in the slide here. This in principle should correlate with the kiln shell, crank, and ovality as well. To do this kind of monitoring, 2 radial displacement sensors are used. But one of the challenges of using radial displacement sensors on the outside of the girth gear are the gear teeth. The sensors monitoring should only look at the top of the tooth surface and not the area between the teeth. So long-term trending can be done to both the measured and calculated scalar values to see how fast the fault conditions are developing and to predict when maintenance and service should be done. In this slide, we see the axial movement being monitored for the girth gear. And it's important to remind you that the kiln shell is not rigidly supported any place and is basically free to slide a certain amount in the axial direction. And this is to allow for thermal longitudinal expansion of the kiln. See, Palle will talk more about this when he talks about kiln axial balance. Now, as a kiln shell, it can actually displace itself as much as 70 millimeters or more during thermal expansion. So it becomes difficult to accurately measure this axial movement with standard displacement sensors. So in this application, 2 axial displacement sensors are used to split the measurement range as shown in the slide. So only one sensor is active at any given time. For example, the purple one on the left is active and the gray one on the right is inactive. And in addition to the axial displacement, the girth gear can also be affected by kiln shell crank, which will create a wobble effect of the girth gear. And this can also be monitored as shown in the figure over here in red. Now, the axial position of the kiln, by the way, is also one of the parameters used for monitoring the axial balance of the kiln, which, as I mentioned before, Palle will talk about later. So we talked a little bit about the radial wobble and axial displacement of the girth gear and how it's monitored. And now we're going to talk about monitoring the pinion. There can be 1 or 2 of these driving the girth gear. Now, the rigidly mounted pinion, it's driven by a motor and a gearbox, is basically monitored by accelerometers mounted on the bearing casing, just like gears in other machines, except there's a need for special considerations to be taken in this case because of its very low speed. For this, special sensors are needed together with special monitoring techniques and signal processing. Because the girth gear can move in all directions, the vibration response in the pinion will also be in all directions. So for this reason, it's necessary to employ X, Y, Z directional accelerometers on the pinion bearing housing. So these can detect gear misalignment, balance, gear mesh anomalies, and bearing faults as well. And this is done by monitoring vibration measurements such as running speed vibration and tooth meshing frequency, which is basically the running speed times the number of teeth on the pinion, and then the individual harmonics of the running speed and the tooth meshing frequency. From a diagnostic point of view, further analysis can be done by looking at sideband energy, bearing fault frequencies, crest factor, etc. Now, in addition to the girth gear pinion, the rest of the drive system is also monitored, which includes the pinion motor and the gearbox, but these are not shown in the slide here. So now we're going to hear Palle talk about the axial balance and the monitoring techniques associated with it.
Yes, so a fault failure mode that we include in our monitoring solution is what we call kiln axial balance. Kiln axial balance is actually a general term that covers all of the forces and the displacement related to the kiln movement in the axial direction. As you see in this illustration, then the kiln is supported by 6 supporting rollers. These supporting rollers can, depending on screwing and inclination, actually exert a force on the kiln in either one of the directions. Also, we have a thrust roller, as you see in the illustration, and this is intended to keep the total load of the kiln due to the inclination in the horizontal plane. So when talking about axial balance, then we want to evaluate basically what is the thrust from each of the supporting roller, what is the direction of the thrust, and also we want to evaluate what is the load on the thrust roller. Also, when the kiln operates, it can have a displacement. We call it kiln floating in the axial direction, and this we also need to monitor. So basically, what we perform in our monitoring solution, that is a specific solution where we identify the thrust from each of the supporting rollers. This is done by thrust-bearing temperature measurements. Also, in order to detect the direction of the thrust, we use displacement sensors for each of the supporting rollers. Additionally, we monitor the load on the thrust roller as well as the position of the kiln. The axial balance is very important. It's a dynamic measure and it changes over time. As mentioned by Michael, then we do see in the industry an increasing use of alternative fuels, which affects the stability and the process of the kiln negatively. This means that thermal effects change more rapidly, coating inside the kiln change more rapidly, which again will change the weight of the kiln. All of this affects the axial balance, which underlines the importance of having a continuous measure of this. This method and this type of evaluation is previously not available in the market. This is something that typically relied on on-site inspections with handheld equipment, but now with this monitoring solution, then we can monitor it continuously.
Alrighty, so Palle, thanks for that, Palle. Okay, now Palle's going to talk a little bit about the kiln service solution. It's not just hardware and software; it's also a solution, service solution, together with diagnostics. And Palle's going to talk about that now.
Exactly, Michael. So what we've seen here is some of the selected failure modes, the theory behind it, and how we have managed to monitor it. This takes part of a commercial offering that we have in FLSmith. This is a extension of what we call level 1 monitoring. This is where we do condition monitoring as a service based on the existing instrumentation that typically already exists on a modern cement kiln. We won't go into details with that, but the interesting thing here is the level 2 package. So this is the solution as referred to in this presentation, where we have the specific developed solution that monitors kiln crank, kiln shear Ovality, kiln drive vibration, and axial balance. And this is a commercial offering that's already running on several of our customers' sites. And on the next slide, I can briefly mention the service model behind this. Compared to many of the other condition monitoring providers in the industry, then we do not only want to provide the data and the instrumentation. Basically, our biggest assets, that's our experience, that's our experience in designing kilns, operating kilns, and maintaining kilns. So what we do is we make a service model where we supply the hardware and the technology and the sensors needed to gather the data. It's based on a cloud application, but most importantly, we have a dedicated monitoring team who monitors the data, evaluates the data, and provides recommendations and proactive actions that the customer can implement on site. So basically, the value is not in the data, it is in our evaluation and our recommendations. So this is a partnership we provide to our customers where we support them in creating more sustainable operations and some of the other benefits as stated in this slide as well. Yes, Mike? So,
So
to
deliverables?
summarize the deliverables in our offering, then it is a online health monitoring solution. And as mentioned, with this, we now provide insight that typically or previously wasn't available. Until recently, these kind of measurements required on-site intervention, typically something that was done as a service every 2 or 3 years. But now we can continuously monitor these health measurements. Then on top of this, we do proactive incident report. That means every time an alert is notified, then we look into it and evaluate the data and provide a recommendation to the customer. In continuation of this, then we do a continuous or quarterly asset health report summarizing the overall condition of the asset, as well as providing long-term recommendations to the customer. As this is a online cloud-based solution, then the data is of course also available online. We provide a smartphone application to the customer called Site Connect, which means they can look up the condition of the kiln no matter where they are, and they can enable notifications if any of these health signals reaches the alarm limits. So all in all, this is the result of the monitoring know-how from Brüel, Kjær, Vibro combined with the machine know-how from FLSmith.
Great, fantastic. Thanks for that, Palle. And you can see the solution, the service solution part plays a very, very important role in the overall condition monitoring solution. Okay, I'm going to have Sascha now. Sascha is going to talk a little bit about from the system side, data flow, the cloud, and I'm going to give it to Sascha now.
Yeah, okay. So I would like just a short overview. How do we get from the sensor signal into the cloud? How do we collect data and how do we transport data? Involved are two devices. That's the VCM3 field monitor. That's the device that collects the sensor signals. It has 12 dynamic signals that are sampled with 200 kilohertz, DC coupled synchronously. Synchronously very important for this application. We have tacho signals to measure speeds. We have digital inputs. We have additional network inputs to go connect to local control systems. So we get additional information like power of the motor and temperatures and similar. We also support multiple protocols, so we could locally provide, for example, the measurement results as an OPC UA or Modbus protocol. The device itself can be used standalone. That means it doesn't need a server to operate and collect data. It has a certain memory size. The device itself is used in several thousand wind turbines and other applications, so we have quite an experience when it comes to remote operation. The device itself is fully configurable via files, so we don't need any proprietary protocol to make binary updates and stuff like that. So basically, FLSmith is able to configure it as needed. The device takes the signals and processes them, and there are two ways to do that. We have the real-time processing, where we produce classic scalar values like overall values, narrowband measurements, similar like any classic CMS system, for a frequency range from 0 Hertz DC coupled up to 80 kilohertz. So we can search for failure modes in a wide frequency range. We process scalar values and provide them to the device, the field agent. Besides the real-time processing that we have in the FPGA inside this processor, we have the possibility to do more complex post-processing. That means that we can collect the DC coupled signals synchronously in certain intervals, and then run up to complex algorithms. We can start with Spectrum. We can do more complex scripts that we can easily deploy and calculate either scalar values or do spectra, orbit plots, or something or similar data. Currently, in the setup, we upload these scalar values, or descriptors as we call them, every 5 to 10 minutes. But that's also on FLSmith to decide how often they want this information. And we provide raw data once a day. That's currently, as I call, around 10 megabyte only. But in case of, let's say, there is an issue with the machine, it's possible to go up to a higher rate for spectral data or for raw data. The data that we have is provided in an open data format, basically JSON files that can then easily be used by FLSmith in their cloud. The other device involved, that's the field agent, that's the FLSmith product. That device is fully integrated into the FLSmith cloud, which means that the configuration of it, the programs, the software is developed in the cloud and automatically deployed to this field agent. The applications on that device are containerized, Docker containers to be precise, and that allows to adapt to data sources that might be a SCADA system with an OPC UA interface that can be down to a simple sensor with a Modbus interface, or in that case, a more advanced interface or protocol for this CMS system. And it's not only the protocol, you can also implement the control of this device. In that case, this field agent can receive commands and control the VCM3 field monitor. The field agent itself can, as I said, collect all kinds of data. It has also multiple interfaces. It has also the function to compress data. And when it was developed, the focus was also to be able to handle bad internet connections, compress data, and persist data. So for this application, there could be several days without internet connection, and we wouldn't lose the information before it is sent up into the cloud. So that's basically the data flow from my side.
Oh, great. Okay, thanks for that, Sascha. So we can see that the system solution and the data management is very, very important to the solution as well, the condition monitoring solution. And so scalability is important as well as accessibility in the cloud. Thanks for that. So now we're going to look at the diagnostics now. And Palle has some slides to present here on some of the results of the monitoring with actual kilns on site.
Yes,
Palle?
exactly. So let's look a little bit more in detail into the data. This first example is on kiln shell Ovality. It's important to mention what we see here is the processed data. So this is not the raw data. This is the scalar values that are calculated based on the sensors on site. So that is the calculation based on tire rotational speed as well as the kiln rotational speed. And the result is this calculation. What you see in the plot here is on the black line, that is the kiln speed, kiln RPM, roughly at 3 RPM, as you see in the y-axis to the right. Then we have the solid blue line, that is the scalar value of the tire migration. The dotted blue line, that is a curve fit trend line. The units of the tire migration is in millimeter. I think accidentally it says micrometer, it is in millimeter. You will see in the plot here some color zones that is in the range from 5 to 25 millimeter. It is colorized green, which meaning it's the acceptable range, between 25 and 30 or below 5 and 0. Then it is in the high value or the low value, and above 30, then it becomes high, so it becomes the critical alert. If we evaluate the live ring migration scalar value here, then you see that it is fluctuating over time. Actually, we see a daily difference, which can be due to the thermal effects. It can even be due to the ambient temperature on site, which changes every day. What's also important is to see that there's a general pattern that the time migration value is increasing, and this is most likely due to the thermal effects and due to the burning process inside the kiln. You will notice also some spikes on this signal. This is unfortunate, some unwanted data, which is happening when we have a rapid change in the kiln speed. A solution for this is being implemented, and that is of course neglected in our monitoring service. So as mentioned, then the time migration value, it changes over time, and this is what makes it important to monitor continuously, especially in the heating up process of the kiln. Then we can see rapid temperature increase on the kiln shell, whereas the tire has a larger mass and therefore takes more time to heat up. This temperature difference can lead to constriction, which means that the live ring migration or the time migration becomes low. On the other hand, increasing coating inside the kiln, increasing wear on the parts can over time lead to increased time migration, which is also an unwanted effect. So what we want to do is to keep the time migration in that acceptable level, and if we see patterns and trends towards any of the limits, then we give active recommendations to the customer on what they can do in order to keep it within the safe range. Yes, Mike?
Okay.
Good. That was an example on the time migration. Then let's look into the Kiln Crank. An example here. Again, let me first explain the graphs as we see. Looking at the left graph, then again we have the kiln speed in black. It is on the y-axis to the right, operating roughly around 3 RPM when it's stable. In this case, we have had some unexpected kiln stops. I can see it goes to 0 at some days. Then we have the solid blue graph, that is the scalar value of the Kiln Crank, and we have a curve fit trend line as well. The value of the Kiln Crank measurements is in micrometer, ranging from 0 to 150, which is the first limit, and above 200, which is the second limit. In this particular case, we see that the Kiln Crank value is somewhat fluctuating, but there's a clear pattern that it is also increasing over time. So in this case, we identified a increasing Kiln Crank and reached out to the customer. So based on this, we did some iterations with the customer, looking into the burning process of the kiln, looking into the fuel mix on the kiln, and based on that, the customer, based on our inputs, they managed to reduce the limit level of the Kiln Crank. And this is basically what we see in the plot to the right. In between the two plots, we have 3 days. So you can see that a general trend that the value of the Kiln Crank is going down, and that it has somewhat stabilized within the acceptable range. Kiln Crank is very interesting because in some case it can actually not be avoided completely. But then what we do is that we monitor and we evaluate what I call accumulated damage. So this is basically for how long time have we had overload and at what value. You could actually see it as the area under the graph. You could see it as the integration of the scalar curve. because this accumulated damage is what eventually will lead to fatigue failures in the mechanical components. So if we have a case where, due to the fuel mix and the use of alternative fuels, that we cannot completely avoid a crank, then what we do is we monitor it, we monitor the accumulated damage, and then we can recommend the customer to do preventive measures as NDT testing in order to check if there are any cracks present in the equipment, or to see if any of the cracks are propagating. So that is the preventive measures in case that the crank cannot be avoided.
Alrighty, thanks for that, Palle. So Ovality and the crank, as we mentioned before, these are kiln shell, some potential failure modes. And I'm going to talk a little bit about the gear drivetrain. And this is the gear drivetrain, as I mentioned before, is the Girth gear, the pinion, and then the motor in the gearbox driving the pinion. So here we see an example of a time waveform for the vibration acceleration signal in the Y direction on one of the two pinions of a kiln. Now, I'm just going to summarize by saying that the time signal is really important for automatically generating as input for generating the vibration descriptors that we'll mention in the next slide. But it's also, time signal is also important for storage for future post-processing analysis. Okay, there are a number of gear drive descriptors that are continuously monitored for detecting bearing and gear faults in the pinion, as well as in the pinion gearbox and motor. In this, on the left here, you can see some of the bandpass measurements for monitoring the running speed and the harmonics, together with the tooth meshing frequency and its first three harmonics. Now these are for both fault detection and for trending. And unfortunately, I don't have any plots to show for this part of the drive system. But in addition to the fault detection, there are also various tools available for vibration analysis. This is used by the FL Smith diagnostic team, such as the FFT plot, which we can see in this slide here. The FFT can be used for identifying the detected fault, determining its severity, and predicting the remaining useful life of the gear or bearing. This particular FFT spectrum is showing some peaks. The lower peaks are basically corresponding to the tooth meshing frequency for the pinion. Okay, there's a lot of other information that could be extracted from the FFT, such as bearing fault frequencies, sidebands, etc. And in addition to that, there are also other diagnostic plots that are useful for, such as the envelope for rolling element bearing fault diagnostics. Unfortunately, I don't have any examples of these in this particular webinar. But okay. So now we come to the end of the webinar, so we'll wrap it up with a conclusion and summarize some of the important key takeaways here. Now, the monitoring service is important for reducing costly kiln inspections, planned and unplanned downtime, and to prepare for hot alignment based on condition monitoring. As in many other industries, there is a greater need to increase production and reduce life cycle costs of the assets, and the kiln is no exception to this. So the monitoring strategy was fundamentally due to the close cooperation development efforts of both FL Smith and Brüel and Kjær Vibro, working towards a common goal of delivering more value to the end user. FL Smith provided expertise in the asset operation and maintenance, while Brüel and Kjær Vibro provided expertise in condition monitoring. Off-the-shelf monitoring solutions were not a feasible option. This is because there has to be a cost-effective and scalable customization to optimize the monitoring solution. And as monitoring experience is gained, the monitoring solution will be further optimized. And ongoing cooperation is still needed for accommodating different kiln applications and for providing additional fault detection and analytics capability as the need arises. As more monitoring data is collected, and there's a lot of it, it can be statistically analyzed to fine-tune the descriptors. Now, the monitoring solution also has to be optimized for data management as Internet of Things concept, the needs for this grow. So the data has to be readily available to the relevant users. It has to be readily correlated with other systems and other data, such as with process data. Because this not only will speed up the process for doing diagnostics and predicting remaining useful life of the components, but it's also for planning maintenance ahead of time. But it'll also increase the reliability of the operation and maintenance decisions. And all of this, of course, has to be done with cybersecurity. And finally, a number of kilns equipped with the advanced monitoring solution have already been delivered globally, and the feedback has been positive on the monitoring results. And there are other projects in the pipeline. So in summary, this monitoring solution represents a breakthrough with kiln predictive healthcare. Most of the critical failure modes can now be monitored continuously and reliably, which couldn't be done until now. Alrighty, so that's the end of the webinar. So I thank my co-speakers for sharing their expertise with you all, and most importantly, I thank all of you all for participating. We are now open for questions.
Excellent. Thank you so much, Michael. Yes, I am here to help us have some question and answer session. We have had several questions come in as you all were presenting today. If anybody does have questions, I encourage you to enter them into your GoToWebinar screen and submit them for our thought leaders to answer. Just as a reminder, we do answer them anonymously on the air. And if we don't make it to your question live, we'll reach out to you after the webinar to make sure that your questions do get answered. So we'll start with one that came fairly early on in the presentation, asking if you are using MEMS accelerometers.
Alrighty, who wants to answer that? Sascha or Palle?
We are using traditional accelerometers, but low frequency accelerometers.
Yeah, MEMS accelerometers are an inexpensive solution for accelerometers, and they are very good actually at low frequency monitoring, but there are limitations. So I think that's the reason for the accelerometers is a standard or normal conventional piezoelectric accelerometers are being used.
So it's specifically selected to match the rather low operational frequency down to 0.06 hertz for the kiln speed frequency, of course, depending on the typical rotational speed. So that is the specification and requirements that we have, and reason for this choice of equipment.
All right, thank you so much, guys, for clarifying on that for us. We'll go ahead and move forward to our next question. Is there any machine learning in order to predict an anomaly condition?
I mean, I can answer that a little bit. I mean, the solution, the condition monitoring solution is still new, basically. I mean, we don't have enough data, basically, for doing AI or statistical analysis. I mean, of course, this would be the intention in the long run as we gather data. So there's just simply not enough data for that right now, but that is, I think, the intention. Is that right, Palle?
Yes, I can elaborate on that. So basically, we have selected some measurements or some failure modes that is well known. So we have well-known limits for these type of measurements. That means we can do active monitoring simply based on threshold limits. Additionally, we use some calculation models in order to detect some of the behavior in the signals. That could be automatically identify a cycle. It could be automatically identify some maximum minimum values, etc. I have had this discussion with many of our customers also, who find it very interesting with AI, but basically what we have is something that's well known and it works already now. And then in parallel, we also do research in more advanced algorithms and AI.
Perfect. Thank you guys so much. We'll go ahead and move forward to our next question. And this is asking about the location. So was the analysis and diagnostics of equipment done locally at FL Smith, the plant base, or remotely by B&K Vibro diagnostic engineers?
Palle, you could answer that.
Yeah, so the pre-processing of the signals is done locally in the BKV equipment. Then based on the scalar values that we export continuously to the cloud, then we do the monitoring centrally from our global remote service center, which is located primarily in Egypt, but also with hubs in India and in Europe.
Perfect, thank you. We're going to go ahead and wrap today up with one last question. They're asking if you have any experience in selective cooling with water sprays of a kiln shell to reduce the amount of kiln crank.
Yes, I'm well aware about that system from another supplier to the cement industry, where the intention is to avoid hot spots, hot areas on the kiln shell by spraying on the water. Potentially the solution works. I'll not question that in this session. It is, however, not something that we have decided to implement in FL Smith. Basically, it is a symptom treatment, and we believe in changing or working towards the root cause to the issue.
Perfect. All right, audience members, if you do have any remaining questions, feel free to continue to enter them as we wrap things up today. As I mentioned, we will pass all the questions along to our thought leaders so they can reach out to you after the webinar to make sure that your questions do get answered. And before we do wrap things up for today, do any of our thought leaders have anything else that you would like to add?
Okay, I can just say thanks everyone for participating. Thanks for the questions as well. And as Jenny mentioned, please send in your questions. I mean, if you have other questions, we didn't have a whole lot of time for a complete question and answer period there. So, but send them in, feel free, and we're willing to share our experience and knowledge in that area. You guys have anything to say?
Thank you for your interest, and thanks for the interesting questions. Feel free to chip in with more.